Section: Introduction. In this section, we discuss the challenges associated with training advanced AI models due to the increasing costs involved. The limitations of Moore's law and Dinard's law for digital hardware have a significant impact on the efficiency of training AI models. This situation calls for the development of specialized hardware to enhance training efficiency. Currently, commonly used optimizers like stochastic gradient descent, (SGD), and ADAM are preferred over more sophisticated optimizers due to their lower computational overhead. Second-order methods, which offer better convergence properties but are computationally expensive, are not widely adopted. To address these challenges, we introduce thermodynamic natural gradient descent, (TNGD), a novel second-order optimization method. TNGD utilizes a hybrid digital-analog approach where a GPU interacts with an analog thermodynamic computer to accelerate the training process. Unlike traditional analog computing methods that are rigid in terms of model architecture, TNGD allows flexibility for users to modify their model architecture using preferred software tools. The analog computer in TNGD leverages thermodynamic processes for computation, which have shown potential for improved runtime and energy efficiency. Our TNGD algorithm is a result of algorithmic co-design, where we have developed an optimizer tailored for a novel hardware paradigm. By incorporating a physical Ornstein-Uhlenbeck process, TNGD implements the parameter update rule efficiently. It offers computational efficiency comparable to first-order optimizers like ADAM and SGD while considering the curvature of the loss landscape with a second-order method. Our experiments demonstrate the competitiveness of TNGD with first-order methods for various tasks. Furthermore, we aim to reduce the computational cost of second-order optimization methods like NGD by leveraging a hybrid analog-digital algorithm. This approach not only enhances training complexity but also aligns the per-iteration complexity of NGD with that of first-order training methods. Section Summary. In this section, we introduce the challenges associated with the increasing cost of training advanced AI models due to the limitations of conventional digital hardware. We propose a novel approach called thermodynamic natural gradient descent, TNGD, that leverages a hybrid digital-analog loop to optimize second-order optimization efficiently. By utilizing thermodynamic processes in an analog computer, TNGD aims to achieve computational efficiency comparable to first-order methods like ADAM and SGD while incorporating the curvature of the loss landscape inherent in second-order methods. Section: Natural gradient descent. In this section, we delve into the concept of natural gradient descent. We are in a supervised learning scenario where our aim is to minimize an objective function. This function involves a loss function L, y, f underscore theta, x, and a forward function f underscore theta, x, that relies on input data and labels. To minimize this objective function, we typically move in the direction of steepest descent, which is indicated by the negative gradient. The natural gradient, on the other hand, considers the direction of steepest descent concerning the Kullback-Leibler (KL) divergence between two distributions. This divergence can be expanded using the Fisher information matrix F. The natural gradient is then determined based on this divergence. For the NGD optimizer, the update rule involves the natural gradient and a learning rate. In practice, computing the Fisher information can be challenging as it requires access to the density function. An alternative is the empirical Fisher information matrix, which is easier to compute. Another approximation to the Fisher matrix is the generalized Gauss-Newton (GGN) matrix, which is beneficial for convergence. This GGN matrix is particularly useful for loss functions of the exponential family. Our methods can be applied to any second-order optimization algorithm with a positive semi-definite curvature matrix. Fast matrix vector products play a crucial role in solving the linear system efficiently. The CG method, known as NGDCG, can be used for this purpose. By leveraging fast Jacobian vector products, we can evaluate the GGN vector product efficiently without explicitly constructing the Fisher matrix. It is important to note that the efficiency of this approach depends on the number of CG iterations needed for good performance. While reaching convergence is computationally expensive, stopping the CG algorithm after a set number of iterations is a common practice. However, due to the sequential nature of the algorithm, parallelizing CG iterations is not feasible. In some cases, especially for ill-conditioned problems, the NGD-CG method may face challenges in getting closer to the true solution after a certain number of steps. Section Summary. In this section, we delve into the concept of natural gradient descent in supervised learning scenarios. We aim to minimize an objective function by considering the Kullback-Leibler divergence between the target and learned distributions. By utilizing the Fisher information matrix, we define the natural gradient as a direction of steepest descent, which can be approximated efficiently using the generalized Gauss-Newton matrix. This approach offers improved convergence compared to traditional methods, especially for loss functions of the exponential family, making it a valuable tool for second-order optimization algorithms with positive semi-definite curvature matrices. Section: NGD with the Woodbury identity. In this section, we explore NGD with the Woodbury identity. When working in machine learning, we often encounter scenarios where the curvature matrix is low-ranked and the linear system to be solved is underdetermined. To address this, we can dampen the Fisher matrix by adding a regularization term, resulting in F plus lambda I. By utilizing the Woodbury identity, we can find the inverse Fisher vector product F caret minus 1, V needed for the NGD update. This approach has been shown to be competitive with NGD-CG when the batch size B and output dimension D_Z are much smaller than the number of trainable parameters n. To implement this method, we need to construct the V matrix, which has a runtime complexity of O, D_Z squared B squared n, and invert I plus lambda caret minus 1, VU, which has a complexity of O, B cubed D_Z cubed. While the batch size usually remains small, the value of D_Z can sometimes make this inversion challenging. For instance, in tasks like language modeling, where D_Z is around 10 to the power of 4, representing the vocabulary size, the inversion process can become computationally intensive. Moving on to thermodynamic NGD, TNGD. This approach combines the computational power of GPUs with thermodynamic devices for solving linear systems efficiently. Previous work has demonstrated that a thermodynamic device called a stochastic processing unit, SPU, can solve linear systems with lower computational complexity compared to traditional digital hardware. The solution is obtained by allowing the SPU to evolve under an Ornstein-Uhlenbeck process described by a stochastic differential equation, SDE. In TNGD, a subroutine estimates the solution to the linear system using the SDE. By analyzing the equilibrium state of the system, we can estimate the natural gradient. The TNGD algorithm involves computing matrices and vectors on the GPU, transferring them to the SPU for equilibrium, and then updating parameters based on the estimated natural gradient. This iterative process continues until sufficient convergence is achieved. TNGD offers advantages over NGD-CG in terms of stability and efficiency. While CG may fail to converge for certain linear systems, TNGD is guaranteed to converge on average for any positive definite matrix. By carefully choosing parameters and allowing the system to reach equilibrium, TNGD provides a stable and efficient approach to optimizing neural networks. Section Summary. In this section, we explore the use of the Woodbury identity in NGD to handle low-rank curvature matrices in machine learning scenarios where the linear system is underdetermined. By dampening the Fisher matrix with a regularization term, we can efficiently compute the inverse Fisher vector product using the Woodbury identity. Additionally, thermodynamic NGD, TNGD, leverages the strengths of GPUs and thermodynamic devices, like stochastic processing units, SPUs, to solve linear systems with reduced computational complexity, ensuring convergence for any positive definite matrix. Section: Computational complexity and performance. In this section, we discuss the computational complexity and performance of various second-order optimization algorithms, including thermodynamic NGD, TNGD. The runtime complexity of TNGD and other similar algorithms is detailed in a table. TNGD's runtime and memory cost mainly come from constructing and storing the Jacobian of f_theta, x, and the Hessian of the loss before sending them to the analog hardware. The analog runtime is denoted by T, similar to the parameter C in NGD-CG, controlling the approximation. The number of model calls for each optimizer is provided, with most optimizers easily parallelizing these calls except for NGD-CG. A comparison of the runtime per iteration for the 4 second-order optimizers is shown in a figure, illustrating how the runtime scales with the number of parameters n and the output dimension d_z. Moving on to experiments, we focus on MNIST classification using a simple convolutional neural network and simulating the TNGD algorithm. The aim is to compare TNGD's performance against popular first-order optimizers like ADAM and explore its behavior concerning analog runtime T and delay time T_d. The training and test losses, as well as accuracies, are presented for both ADAM and TNGD, showing that TNGD outperforms ADAM, especially in the initial stages of optimization, and generalizes better. The results indicate that even with a smaller batch size, TNGD performs well, showcasing the benefits of its continuous time nature in smoothly transitioning between first and second-order optimization. By adjusting the analog dynamics time and delay times, TNGD's performance can be further improved, resembling momentum effects in optimization. Section Summary. In this section, we analyze the computational complexity and performance of various second-order optimization algorithms, including thermodynamic NGD, TNGD, which focuses on constructing and storing the Jacobian and Hessian of the loss function. TNGD shows promising results in terms of runtime efficiency, with the potential for a significant speedup over other second-order optimizers, especially for intermediate values of output dimensions. Additionally, experiments on MNIST classification demonstrate that TNGD outperforms popular first-order optimizers like ADAM, showcasing its effectiveness and generalization capabilities, even with smaller batch sizes. Section: Language Model Fine-Tuning. In this section, we explain how we can use thermodynamic NGD for language modeling tasks in more practical scenarios than MNIST classification. We focus on the Distill-Burt model, which we adjust on the Stanford Question Answering Dataset, SQUAD. This dataset is commonly used to assess a model's understanding of technical topics through answering questions based on extracted information. When fine-tuning the model, we implement a low-rank adaptation to reduce the number of trainable parameters to a manageable level, around 75,000 in this case, suitable for limited computational resources. In our analysis, we compare the training loss using different optimizers. The basic TNGD approach performs worse than ADAM in this setup. However, a combination of TNGD and ADAM, known as TNGD-ADAM, where the natural gradient estimate works alongside the ADAM update rule, shows the best performance. One reason for this outcome could be the dual preconditioning of the gradient in TNGD-ADAM. The first preconditioning involves curvature information from the natural gradient, while the second comes from the ADAM update rule, which adjusts the natural gradient values further. We also observe that increasing the analog runtime enhances the performance of TNGD-ADAM, similar to our previous findings. The analog runtime in TNGD can be seen as a valuable computational resource since it is very cost-effective, as time constants can be made very small. However, the practical implications of our work depend on the availability of analog thermodynamic computers, like a larger version of the system mentioned in a reference. We provide a circuit diagram of a potential thermodynamic computer in the appendix, which can utilize standard electrical components and benefit from CMOS-based fabrication infrastructure, making scalability likely, although this still needs to be proven. Analog computers often encounter precision challenges, where the accuracy of solutions is limited by the precision of electrical components. For analog thermodynamic computers, this issue can be mitigated using an averaging technique, which can be directly applied to improve solution accuracy in the TNGD algorithm. Despite potential precision-related errors, training-based applications may exhibit a high tolerance to such issues, although further investigation is necessary to confirm this hypothesis. There is a growing body of research suggesting that high numerical precision is not essential for good performance in machine learning, particularly in very low-precision inference and training scenarios. Additionally, thermodynamic computers are expected to be resilient to stochastic noise sources, as stochasticity is a fundamental aspect of such systems, as demonstrated in the appendix. We have conducted numerical tests on TNGD for a few tasks like MNIST classification and Distill-Burt fine-tuning on the SQUAD dataset for a limited number of epochs. Therefore, exploring whether the benefits we observe for TNGD extend to other applications is a crucial next step.